Hello, and firstly welcome to the 11th Annual Information Technology, Electronics and Mobile Communication Virtual Conference held in Vancouver. My name is Daniel Mitchell and I am a postgraduate research assistant at the Smart Systems Group based at Heriot-Watt University, Edinburgh, Scotland. The following work is a partnership between the Offshore Robotics for Certification of Assets Hub, Microsense Technologies Limited and the Smart Systems Group. Today I am delighted to be presenting an evaluation of millimetre-wave radar sensing for civil infrastructure. A brief overview of this presentation includes frequency modulated continuous wave FMCW radar for non-destructive evaluation, where the general benefits of FMCW technology is discussed. Next, the technical challenge which engineers face when evaluating the integrity of civil infrastructure is presented. Then I outline the solution to the technical challenge and value created from millimetre-wave sensing. The laboratory-based experiments are then presented within this presentation, where each experiment discusses the procedure and results directly afterwards. Experiment 1 is titled Embedded Material Analysis in Sand, where a copper rod and a copper sheet are buried inside the sand pit to evaluate FMCW sensitivity to a number of variables. Experiment 2 investigates embedded material analysis in Darney Sandstone for radar sensitivity to embedded metals and fluid ingress. Lastly, Experiment 3 follows for the embedded material analysis of different types of sandstones, which are buried within the sandpit. This presentation is rounded off by highlighting a technical summary of the observations found. Finally, our presentation concludes and invites you to view any of our parallel work via our online portfolio alongside our author biographies and project contact details. To provide an overview of our unique and patented method of sensing, several benefits for engineers and robotic platforms have been outlined. The sensor can be utilised for non-contact and non-destructive analysis, is highly tunable in terms of range, field of view and depth of view, one data acquisition per second and sub-second if required, requires low power, is of military specification, and highly integratable into existing systems such as robotic platforms or installation within infrastructure, is suitable for metallic targets which can provide external state of health, suitable for composites and low dielectrics for internal state of health measurements, has the ability to produce real-time results on a platform-mounted or handheld device, and lastly, operates accurately in poor lighting and opaque conditions such as smoke, steam and mist. So, the technical challenge. How do we address maintaining a large complex infrastructure which provides essential services such as energy, transport, water and waste management? Civil infrastructure requires a cyclic integration of design, construction, inspection, repair, maintenance, renewal and upgrading to ensure safety and meet societal requirements to access resources. This could be compared to as the circle of life of operation and maintenance. Reinforced concrete has many benefits for construction, however is prone to early deterioration due to the effects of carbonation, which is a reaction with carbon dioxide, and chloride polluted concrete due to salt. This results in corroded reinforced concrete which can significantly deteriorate the integrity of a structure. Current investigations of civil infrastructure are unreliable and do not give an accurate representation of the integrity of a structure. This is due to civil engineers relying on visual inspections and acoustic emissions. Many problems start off internal to the structure and do not display visual cracking until a severe amount of deterioration has formed. So how do we solve these technical issues? The development of our FMCW radar presents a unique method of non-destructive evaluation for fault prognosis of embedded rebar. This method of sensing has been demonstrated in the following laboratory-based experiments which examine the return signal amplitude received at the radar. The sensing method enables for distinct subsurface material responses and properties which are not visible externally, hence early detection of faults within a porous structure. The value created by millimetre-wave sensing and this research looks to reduce risk and operational costs via proactive risk mitigation. The first experiment conducted included embedded material analysis in sand. The aim of this experiment was to investigate the return signal amplitude of buried materials within the sand by utilising non-destructive evaluation for A. the shape of embedded material, which features a copper sheet and a copper rod, and B. the depth of embedded material. The FMCW radar was positioned 10 cm from the surface of the sand. The test material was then buried at incremental depths. The FMCW radar was then initiated where the results are displayed in real time for the return signal amplitude. The graphs we are viewing currently are the fast Fourier transform with the return signal amplitude against the bandwidth sweep in the frequency domain, otherwise known as the bin numbers. The bin number, which we are most interested in, is where we receive the main reflection from the embedded material. Hence, bin 9 is focused on within these figures. Figure 2 on the left-hand side shows results for the embedded copper sheet, where figure 3 on the right displays results for the embedded copper rod material. It is important at this stage to highlight that the copper materials are completely buried at each set depth for each run of the experiment. Therefore, the material is not visible from the outside of the sandpit. These results display that embedded material return signal amplitude decreases incrementally as a function of increasing the burial depth. This is observed for the copper sheet in figure 2 and copper rod in figure 3. This decreasing trend in return signal amplitude is due to more grains of sand being between the radar and copper sheet, therefore scattering and absorbing the signal to the receiver. Figure 3 highlights a similar trend for the copper rod buried at different depths within the sandpit. The copper rod, however, has a much smaller surface area, therefore returns a much lower return signal amplitude when compared to the copper sheet at each embedded depth. These results enable for detection of depth of embedded material. Lastly, the return signal amplitudes were then compared against each other for the copper sheet versus copper rod. The results indicate a distinct difference in return signal amplitude at different depths, depending on the shape of material. This enables for detection of shape of an embedded material and therefore potential characterization by development of a library for the copper material and shape. These differences are verified at different depths. This experiment was also repeated for different materials including aluminium, brass, and iron. The second experiment was designed to identify if the FMCW radar was sensitive to embedded rebar within Darney sandstone. An aperture was drilled into the Darney sandstone so that materials could be easily inserted to simulate different types of rebar and other scenarios. As viewed to the right of figure 5, the antenna was positioned 10 cm from the target interface on the Darney sandstone. A dulled drill bit, stainless steel ruler and 3 ml of water were used to investigate if the FMCW radar sensor was sensitive to these variables. First, the FMCW radar was given time to establish a baseline measurement. Next, the dulled drill bit was inserted into the rear of the aperture. The dulled drill bit was then moved closer to the antenna to the near side of the aperture. Next, the stainless steel ruler was positioned inside the aperture as pictured currently. The stainless steel ruler was then repositioned so that the concave side was facing the antenna. Both stainless steel ruler and dull drill bit were then removed from the aperture to allow for 3 ml of water to be inserted onto the wall of the aperture using a dropper. This was then allowed to dry naturally at room temperature. Figure 5 displays the return signal amplitude on the left y-axis and the return signal phase shift on the right y-axis. The main reflection, or peak, from each frequency sweep was then recorded and is now displayed on the graph as a blue solid line. What we can identify is on the lead up to marker 1 at approximately 2.5 minutes, the baseline measurement for the Darney sandstone and aperture is being established. As the dulled drill bit is inserted into the aperture, there is a slight shift in the return signal amplitude and phase shift as indicated at point 1. As the dulled drill bit is moved to the near side of the aperture, there is an increase in return signal amplitude at point 2. At marker 3, the stainless steel ruler is added within the aperture. There is a large increase in return signal amplitude and the phase shifts markedly also. With the stainless steel ruler reorientated in the aperture with the concave side facing the antenna, the return signal amplitude increases further and phase shifts significantly also. Before point 5, the ruler and dull drill bit are then removed from the aperture, where enough time is given to allow the baseline to re-establish itself. At point 5, 3 milliliters of water is sprayed on the wall of the aperture using a dropper and allowed to dry at room temperature. From this result, we can identify that the return signal amplitude and phase each shift dynamically and is due to the water seeping into the pores of the sandstone and evaporating at room temperature. The previous experimental setup in Experiment 1 was utilised again to determine if the FMCW sensor was sensitive enough to detect and distinguish between porous structures such as sandstone, which are embedded within the sandpit. Due to the limited depth of the sandpit, the experiment was constrained to a layer of sand which measured 3 cm on top of each sandstone. The Darney sandstone and Lazenby sandstone were buried within the sandpit where the return signal was compared for each. Figure 9 displays the return signal amplitude of the sandpit baseline reference, Darney sandstone and Lazenby sandstone, once again focusing on bin 9 due to the main reflection from the interface of the sandstone. First, it is important to understand the properties of Darney and Lazenby sandstone. Darney has a porosity of 18.7% and contains relatively well-sorted subangular quartz silicon dioxide grains of fine to medium grain size of approximately 125 to 350 micrometers, with subsidiary orthoclase feldspar and clay present within some of the pore spaces. The Lazenby, on the other hand, has a significantly lower observed porosity at 11.6%, which is considerably lower than the Darney sandstone. This is due to the sample being dominated by highly cemented, grain-supported, fine to medium-sized spheroidal, sub-rounded grains and well-sorted quartz clasts ranging between 200 to 500 micrometers. The Lazenby sandstone contains mainly quartz and orthoclase feldspar with some clays and very much the same proportions of the Darney sandstone. However, the iron content is more dispersed throughout Lazenby when compared to Darney sandstone, although the magnitude is similar. The figure highlights a distinct return signal amplitude for Darney sandstone against the Lazenby sandstone, which enables for FMCW detection and characterization of subsurface materials. The implementation of FMCW radar sensing enables for non-destructive evaluation of subsurface properties. This leads to enabling for previously inaccessible information for inspection engineers. The experiments within this presentation have demonstrated the following: the detection of depth and shape of an embedded material, the detection of metals and water ingress within a porous structures, in this case sandstone, and lastly, the detection and characterization of subsurface embedded materials in sand. These experiments has enabled the team at Heriot-Watt to better understand the possibilities and applications where the FMCW radar can aid non-destructive testings. Recent tests have already proved that FMCW radar sensing can distinguish between a sample of metal which is corroded and uncorroded. This work was expanded on by detection of corrosion under insulation of paints. Therefore, the future development of the sensor will include detection of corroded iron rebar within a porous structure. Another avenue of research we will also be considering is the detection of subsurface cracking within civil infrastructure, as this can lead to significant deterioration in structures. At this point, I would also invite you to view Dr. Jamie Blanch's presentation, who is also part of the Smart Systems group and presenting at this conference. This presentation utilises the same FMCW radar setup, however, is being developed for structural health monitoring of wind turbine blades. The presentation is called Asset Integrity Monitoring of Wind Turbine Blades with Non-Destructive Radar Sensing. You can also visit our YouTube channel, Smart Systems Group or Orca Hub websites to view our latest research presentations, public outreach and news features. Simply search for Smart Systems Group Heriot-Watt University or OrcaHub in the YouTube search bar or Google, or follow the web addresses above. We invite you to view our other published research outputs or ask us any questions. The next slide features all of our key contacts at OrcaHub. Thank you for watching, and we look forward to future engagements.